Hello and welcome back to Differential Equations, section 7.2 on transformation of initial value problem. This is where we learn to transform differential equation using Laplace transform and cast it into that very easy algebraic equation so we can solve it easily. Now, what is actually happening here? Well, you are going to have a differential equation. Actually, this box needs to be much bigger because I need to say with initial condition. So you have to have that, x of 0 equals 7 and blah, 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 right? So you have to have that. Otherwise, you can't do Laplace. Then you are going to use the Laplace and transform that into a Laplace domain equation, which actually is algebraic equation. Then you will solve that algebraic equation. And then once you solve it, you will have to, in 7.3, do the inverse transform. To go back and have your answer as x of t equals whatever it is, solution. So we transform our differential equation into algebraic equation. We solve algebraic equation, which is literally just adding and subtracting numbers, dividing and stuff like that. And then you have to do inverse transform, which is 7.3, which is why we need to review all of the integration techniques and stuff, including some tricks possibly, but 99% of the problems are all partial fraction decomposition. We're going to deal with that tomorrow for those of you interested, obviously. And then you will, once you do the inverse transform, which is 7.3, you will finally have the solution of the differential equation right given. Now our job is to learn how to transform this. So here to here is 7.2. Here to here is basic algebra, like literally algebra 1. And then inverse itself is going to be 7.3, and then solution is just a solution. So that's what we have. So let's learn 7.2, which is the way to transform this. So what we are going to do is we're going to have our standard, you can do constant coefficients, a x double prime of t plus b x prime of t plus cx of t equals f of t, with x of 0 equal x0 and x prime of 0 equal x prime 0. So these are your initial conditions. I kind of don't like this notation. I would rather put, y or something, but such is life. Now, you're going to apply Laplace. So when you apply Laplace transform, you get a Laplace of x double prime of t plus b Laplace of x prime of t plus c Laplace of x of t equals Laplace of f of t. Clearly, we need to learn these transformations. You're good here, you're good here. You know what these are. These two were done in 7.1. You look at the tables, right, and you're done. These are the new ones. And that is what we are learning today. So the transform of any derivative, so this is, right, general form, meaning any derivative. So Laplace of any derivative, Laplace of f any derivative, there we go, much better, is going to be s to the n Laplace of f of t minus Sn minus 1 times f of 0 minus Sn minus 2 times f prime at 0 minus dot 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 minus Fn minus 1 of 0, which is easier to write as Sn times f of s minus Sn minus 1 f of 0. Guys, this is your initial condition. This is your x0. This one. It's just a number, nothing special there. It looks bad, but it's actually a joke, which is why engineers love it. Minus Sf n minus 1 at 0 minus f n minus 1 at 0. So it kind of looks bad until you start figuring out technically the only two derivatives you need, which are the first and the second one. If you really want to, go into third one, you can go into the seventh derivative as well, because the formula is a pattern. It's a joke once you understand the way to read the formula. So now, what are the two that we actually need? We need first and second derivative. So for the first derivative, your Laplace transform of the first derivative is simply s times the Laplace transform of f of t minus f of 0. That's s f of s minus f computed at 0. That's it. And the second derivative is Laplace of the second derivative. And you can read that from the picture here. Because look, if your n is 2, because the second derivative, then it's s squared Laplace, and then the first and the second over here. So it is s squared Laplace of your f of t minus s f, as you can see over here. Now you're here, right? So that's going to be s times f of 0, and then minus the next one is taking 2, so there's no s, and it's just f prime of 0 for the second derivative. So if you want to write that in the simple notation, it's just this. So these are the two formulas that you will be using. Again, you can make this easily for the third derivative and the fourth and whatever, because all you need to do is to put this n to be, let's say, 4, in which case that's a 4, right? And that's a 3, and that's a 2, and as you go, right, because you're subtracting 4 minus 1 is 3, 4 minus 2 is 2, and so on. So the formula is actually a joke as soon as you get used to it, right? And now obviously for the fourth derivative, you will have four of these, so they will just plug in. And as you can see, your S goes 4, 3, 2, 1, 0, and your initial conditions start the basic one, then the derivative, then the second derivative, and the third derivative conditions. So it's not that bad. So once you know the formulas for conversion of the derivative, what's left is to just convert the system. Now, we're going to talk about the easy system, which we can check with another method, just, because we can. And we can start, let's say, with x double prime minus x prime minus 6x equals 0, where x of 0 is equal to 2 and x prime of 0 is equal to -1. Now, these are initial conditions, so these are zeros because initial means when the system is put in motion for the first time. That happens at time equals 0. So we are starting there. Now, what do I need? I need to Laplace the whole thing, right? So when I do the Laplace in here, I will get Laplace of x double prime minus Laplace of x prime minus Laplace 6 Laplace of x equal to 0. Now, Laplace of x is your f of s. That's that one. So that goes in here, right? That's the easy one. But we have to deal with the derivatives first. So what do I have? I have a second derivative. See, second derivative, that's this. So I need all of this cut and paste for the second derivative. Let's go. That's going to be, and I'm going to actually underline that blue and I'm going to color code it so you know what is from where. So we have s squared f of s minus s times 2 minus -1, and that is the blue part. Then we have minus, and then we have Laplace of the first one, which is this mess. So that's f of s minus 2. So s f of s minus 2, and that is going to be my orange. And then I have minus 6 f of s. Let's call that one green. Everything equal to 0. So now I simplify this, remove parentheses, right? So now it's algebra. Minus 2s plus 1 minus s f of s plus 2 minus 6 f of s equal to 0. So collect the entire s f of s deal. So when I factor f of s, the leftovers are s squared minus s minus 6, and the rest is minus 2s plus 3, right? The 1 plus 2 gives you a 3. So now we move these two to the other side, and then we divide by this one to get fs alone. So fs times s squared minus s minus 6. Be very careful with your 5s and your s's. 5s, sharp edges, not sharp edges, right? Because I've seen a lot of grade dies, due to this becoming 25 when it's actually 2s. So be very careful about that. It sounds funny now until exam anxiety kicks in and then you start making those mistakes. So pay attention. So this is 2s minus 3 divided by s squared minus s minus 6. And guys, that's it. Because the inverse Laplace transform of this one, right, is going to give you your x of t, or whatever the hell it was. Yeah, it was x. And then whatever the inverse of this is, will give you the solution. So what we did is we transformed the differential equation into something that was actually algebraic equation. And then all we did is we collected like terms and we moved the polynomials here and there, which is just basic algebra. We did not take any derivatives, no integrals, no complicated techniques like, right, those forever undetermined coefficients and blah, blah, blah. Everything was done very, very clean, very easy. And this is why a lot of professors later on in your chemical engineering, mechanical, electrical will line up problems so they are easily solved by Laplace rather than all other methods. So you can get through, most of your work later on in these engineering courses. You can get by just with Laplace. And when you get stuck with Laplace or something, you just use the power series and just destroy that problem completely. Obviously, power series is going to be the most powerful way to do these things, but it's also the messiest and hardest to understand, whereas it's with all most powerful techniques for literally anything. But the trick is that, if you know it, then the rest of, math is a joke. All right, so now the question is how to deal with this inverse. Now, guys, one more time, we started with the differential equation right here. We transformed that differential equation using Laplace transform into what is algebra. And just by moving terms to the other side, dividing by polynomial, which is again shoveling algebraic expressions, we have the solution. This is the Laplace solution to the problem. This is the solution in frequency domain, right? The problem is solved, except that the solution is a frequency domain. So this is equivalent of you solving the u sub problem and getting the answer like e to the u plus 1 plus c. And now you have to plug u back in to go back to x, right? If you remember your u sub, you know that you transform the problem into u, so it's a joke to solve it. And then once you solve it, then you put x back and you present your answer in terms of x. So this is the same thing. We transform the problem into Laplace, or using Laplace transform into a frequency domain, and we just solve the problem. So the problem is done. Now all I need to do is to bring this back into a t variable, t domain, which is a time domain. So now I just need to do what we call inverse Laplace over here. And once I apply inverse Laplace transform, it will give you the original problem back. So when you have some kind of an expression, right, you will use Laplace transform to go from time domain into what we call frequency domain, and then you will use inverse Laplace transform to go back. Now, guys, inverse Laplace transform is literally reading that table of values backwards, but the issue is obviously that you have to use partial fraction decomposition. You have to use those, fixing the constant like I showed you the last time. Like, you have to use some kind of mathematical witchcraft to get through these problems, because they are not, like, you're not going to find what you see here. You're not going to find this in the table ready to be converted, right? You have to fix it. Now, how do you find inverse Laplace transform? Okay, so to find inverse Laplace, first what we have to do is factor the bottom. So the bottom is going to factor over -3 and +2. Because when I multiply -3 and +2, I get -6, and then -3 + 2 is -1. Good. So this is what we have. This is what we have. And now, again, one of the cheaper techniques is to use partial fraction decomposition. Now you say, well, wait, if that is cheap, then what do the bad ones look like? Well, 7.3 is coming up. Don't run that much ahead. So we start by partial fraction decomposition. And again, if you're not remembering this from Calc 2, because it's been, let's say, a year, or you have a Corona Calc 2 grade, right, which means you passed everything, have zero knowledge in it, then in that case, make sure you don't miss tomorrow's review on Calc 2 concepts needed to survive chapters 7 and 8. So now, partial fraction decomposition over here is going to make those two fractions. These, in this case, they're both linear, and that needs to be equal to this. Now, I have seen students change these s's into x's and things to so they're not confusing s and a 5. And I'm gonna say, do whatever hell you want. Just make sure that you know that the answer is s, because we still have to bring it back into a t using the tables. But when you have something that matches the tables. So we know we are supposed to cross multiply this, so that's going to be as plus 2a plus bs minus 3b divided by s minus 3s plus 2 equal to 2s minus 3 over s minus 3 s plus 2. Now you see that the denominators just drop when you multiply through with the same denominator, and you are left with the top. You factor out s, so it's a plus b times s plus 2a minus 3b equals to 2s minus 3. From here, you equal the coefficients. Hello, linear algebra. You equal the coefficients and you make your a plus b equal to 2 and 2a minus 3b equals to -3. And you can solve for a and b. This is now basic elementary algebra system. Now, whether you want to do substitution, elimination, Gauss-Jordan elimination, row reduced echelon form for matrices, no one cares, right? Just do it, right? Now, some students will say, oh, multiply the top one by 3 because that will kill b. Fine, do that. So when you multiply the top one by 3 and add them, you will have 5a, b's are gone, and then 6 minus 3 equals to 3. So a is 3/5. One more time. 3a plus 2a is 5a. B's cancel because you have plus 3b minus 3b. And then you have a 6 minus 3 is 3. You divide both sides by 5 and you get to 3/5 over there. So if a is 3/5 and the b must be 7/5, right? So they can add to 2 because 7 plus 3 is 10 divided by 5 is 2. So we have our a and b, and now we go back into our fs and we say my a is 3/5, and that was divided by s minus 3, and my b is 7/5, and that's divided with s plus 2. Now, when you hit both sides with the inverse Laplace, your f of s becomes x of t. And now you have to find in your table, what fits these? Well, if you, again, flip your book, right, to the front cover, or you printed from the internet the table of Laplace transforms, in the table you find that e to the at transforms into 1 over s minus a. Well, that matches this perfectly once you kick out the 3/5. So 3/5 e to the 3t. Now, the second one is a little bit trickier because it's negative 2t. You see, your formula has a minus. So if you have s plus 2, I can't believe I'm talking about this, s minus minus 2, which means that a is negative 2. Here's your solution. You move along with your life. Now you will say, Professor, that was really not worth it because we could have just solved this problem with the R method and be done 30 minutes ago. Yes, you don't even use, but you also don't use the sledgehammer when you have to hang the painting on a wall for a little small tiny nail, right? You don't use a sledgehammer for that. You have a little, nice hammer, right? And I mean, you could use the framing hammer as well, right, to hit the nail in the wall to hang a picture. But you're definitely not going to use a 40-pound sledgehammer to do it. I mean, you can. You just seen it. You just seen me use a 40-pound sledgehammer to solve this problem, because that's what this is. A lot of unnecessary work for a very simple problem. But once you realize that this method completely eliminates your undetermined coefficients and variation of parameters and all of those other horrors that we went through, all of a sudden this method becomes, right? Because those calculations are way worse than this. I mean, remember undetermined coefficients? Well, you should remember because you have exam coming up in 10 days, right? On undetermined coefficients. So you better remember them, right? So again, we learn Laplace transform so that we can make life much easier in terms of these problems later on. And you can go and get technically any of these, mechanical systems and all of this stuff, because you can always convert these into Laplace. And when you convert them into Laplace, like if you have a system of equations, we'll do that as well. When you have systems of equations, those are systems of differential equations. Once you transform those into Laplace, you have system of Laplace equations, and those are algebraic equations. You don't need any of the eigenvalue or any of the horrors that we went through there, because you are literally solving the system of two algebraic equations at that point. And once you solve those, right, you just convert them back using inverse Laplace into those solutions directly. Now, granted that inverse Laplace is going to give you some, right, some trouble, because you will have to use the methods of splitting fractions, partial fraction decomposition, even the trig sub, and depending on what kind of horror you get in that algebraic equation. But to solve the system, I mean, it's way easier than what we had in previous chapters, which is why, again, this is used literally everywhere. So we can take a look at another problem. Let's use one of the problems. We just jump into homework real quick and take a look into one of these problems that you would have to use. Oh, perfect. There we go. Whole bunch of them. So for this problem, you have to use undetermined coefficients, right? If you do them, so this is one of those mechanical problems where you have oscillation, right? We see that by writing this, and then you have the forcing term of cosine t and initial condition that the object starts at 0 with initial velocity also 0. And then when you kick the problem to move, there is your cosine t, which will be supplying the energy and keeping this oscillation going. And because there is no x prime term, which is the dampening, this means that this system will never stop, right? It will be oscillating forever. We know how to solve this, right? This is your exam 2 question, right here. There we go. Exam 2 question. All you do is you do the R equation on this side, and then you do undetermined coefficients, and then when you have the solution, use these two, write in those derivatives, and right 2 pages later, there is your solution. Easy peasy, right? Now let's see what Laplace is going to do. Laplace is going to say, okay, I have to transform all of this in one shot. So I'm going to Laplace x double prime plus 4 Laplace x is equal to Laplace of cosine t. I'm just going to look in a table, obviously. You know, it's like your crystal ball. You know what's there. And now all I need to do is to, again, go back into my equations and write everything out. Now, both of these are zeros, so that's going to be, right, interesting. We have s squared f of s minus s f of 0 minus f prime of 0 plus 4 f of s, right, is equal to, and then you look at the Laplace, right, the cosine is the one that has the s on top, so that's going to be s over s squared plus 1 because coefficient of t is 1. That's your k. I hope you studied. Now, both of these terms go to 0 because they are zeros up there. And you are left with s squared f of s plus 4 f of s is equal to s squared plus 1. So factor out your f of s, which gives you s squared plus 4, and you have s of s squared plus 1. When you divide or multiply both sides by 1 over s squared plus 4, here's your solution in frequency domain. Right? That's it. And now, all I need to do is to figure out how to split this up using inverse Laplace to work out my solution in the time domain, which is x of t. Now it's going to be, again, partial fraction decomposition. And for that, again, Calc 2. So again, we will be reviewing this stuff tomorrow evening if you are having trouble. I mean, you did vote. You wanted one. So yeah, be there. All right. So what do I have here? Well, now I have as plus b over s squared plus 1 plus cs plus d divided by s squared plus 4 is equal to s over s squared plus 1 s squared plus 4. Guys, again, there will be no undetermined coefficients in this case. Laplace is just going to chew up through everything in one shot and give you the answer that it's done and done, initial conditions and those C's computed, everything done. The only annoying part over here is that you have to go through inverse Laplace. But again, there's never free lunch, okay? So now you gotta cross multiply everything and then work that out. So what do I have? I have as cubed plus bs squared plus 4as plus 4b. That's when I multiply this. You have to have 4 terms because you are multiplying 2 binomials. And then we multiply the other. So plus cs cubed plus ds squared plus cs plus d equal to, right, all of this. We have s squared plus 1 s squared plus 4 equal to s over, and then same parentheses. Now the parentheses will cancel, and you get your, you have to factor your cubes, factor your squares, factor singles, right? So you have your a plus c s cubed plus b plus d s squared plus 4a plus c times s plus 4b plus d, everything equal to just s. All right, so a plus c is 0 because there is no cube term on this side. B plus d is 0. Again, there is no cube on that side. However, 4a plus c is equal to 1 because coefficient of a linear s, right, is 1. And then you have 4b plus d equal to 0. And as you can see, the only equations that matter here are the first and the third equation, because if b plus d is 0, that says that b is equal to negative d, right? And then when you plug that in over here, you will get that b equals d equals 0. If you don't believe me, just go and do it. So once you figure that out, you are left with a plus c equals 0 and 4a plus c equals 1. Now, when you subtract these two equations, you get 3a equals 1. A is 1/3. And if a is 1/3, then c better be negative 1/3 so they can add to 0 from the first equation. And you also have your b and d are 0. So you have your 4 coefficients, and now you can go back into your setup, which is this, and plug those values in. Again, more on this, right, when we review, because again, this is all Calc 2 now, has nothing to do with differential equations. Oh, come on. There we go. So now, this setup becomes a is 1/3, so 1/3 s divided by s squared plus 1 plus negative 1/3 divided by s squared plus 4. So that's your f of s. So your f of s is equal to 1/3 s squared plus 1. You see what I did with the fraction. I put it in front of the expression that I'm going to use for Laplace, inverse Laplace. And then I put minus 1/3 over here, and then I have 1 over s squared plus 4. And this is where I apply inverse Laplace. Actually, I'm going to use different color for this. So now that I have this, I apply inverse Laplace, right? So that has that minus 1 on top. So when you hit this with inverse Laplace, you get your x of t, and then you got your 1/3, and then you have your f over s squared plus 1. So now you can find this in a table, right? Because s over s squared plus 1, and then there is a s on top, which means that this has to be a cosine, and the k is equal to 1. So this is just cosine t. Minus 1/3. Now we have an issue. We know that for sine, this is your k squared, you have to have k on top, which means that if you have s squared plus 2 squared on the bottom, you have to have 2 on top. So in order for me to transform this second one, I need to multiply 2 and 1/2 in front, right? Which changes this 1/3 into 1 over 6. And that's going to be sine 2t. And now the problem is over. Observe that your C1 and C2 are already in there. You also have both of these parts, one that is from the undetermined coefficients, the other one that is from the characteristic R equation. So all of this stuff, right, works. I'm just going to put this sine kt transforms down into k over s squared plus k squared. Just wanted to make sure that so you know why I had 2 squares, which means I need a 2 on top. Why I did the red 1/2 and a 2. This is way cheaper than undetermined coefficients. And it goes across the board, right? You are going to have the same stuff happening. Guys, and even the repeated ones, right? Remember how much that was the annoying thing to do, the repeated roots? Yeah, this makes that joke too. So when you're not going to use this? Well, you're not going to use it on a problem like this. Because this one you can pretty much solve just by looking at it. Right? You look at this problem and you say, oh, that factors over -3 and 2, so my answers are e to the positive 3t and e to the -2. Like, just by looking at the problem, you know what the answer is. There is no reason to go through Laplace for a problem like that. But that's because it's 0 here, so it's a joke, right? We don't need undetermined coefficients or variational parameters. But the next problem, right? If we do Laplace, we get to bypass everything. Now I did not do the colors here, so here are the colors. So this way we have everything color coded in terms of transformations, like what piece is from where. Let's see another. There is this cool formula. I don't want to skip over it. It saves you calculations. I call it cool formula. It's something that, you know, you learn if you want to skip some work eventually. T e to the at is equal to 1 over s minus a squared. And you go, oh, wait, that was the repeated one. Yes, that was the repeated one from the, right, because you see the form over here. You pre-multiply by t. And then if you have another repeated one, it's t squared. Guess what happens, right? I'll let you discover that. So that's a really cool part. Now let's take a look at another exercise from homework. How about one of these systems? How about one of these systems? x prime is equal to x plus 2y, and y prime is equal to x plus e to the negative t. Well, that was a nice and evil. So x of 0 equals 0, y of 0 equals 0. See, this one over here makes you do the undetermined coefficients for systems, right? And we all know how much you love that one. So here is the cool way that the Laplace is dealing with this, so you don't have to worry about these things later on. So your job is to get the Laplace of these. So you have two functions now, and before you had f go into capital F. Now we're going to have the x go into capital X and y go into capital Y. So make sure that you have your x's clearly different, because y is easy to kind of see, but if you are sloppy and you're not writing your capital letters, you're going to get confused. Now I do also suggest to students, to do this for capital X and leave the lowercase x this way. And if you want to be a little bit more particular, you can do that as well. Just please don't do this and then you don't know which one is capital, which one is lowercase. So make sure that you can differentiate between them, because I'm going to now make this statement that Laplace of x of t is going to be given as the capital X of s, and Laplace of y of t is capital Y of s, because that's the notation, right, that I'm going to use. And here we're going to hit both of these with Laplace. So the top equation is the first derivative, so it's s x of s minus 0, because you have that condition right there, is equal to x of s plus 2y of s. Straight conversion of x, right? Just capital X and y is capital Y, and you just multiply that 2 in there. Now for the bottom, you have again y prime, that's going to be sy of s minus 0, this one, is equal to x of s. And now plus, you have to use the table, if you remember that 1 over, right? So e to the at converts into 1 over s minus a. So that's just going to be 1 over s plus 1. I hope you remember that. So what do we have here, right? Well, move everything that has x and a y on the left and everything that has no x and a y on the right. So I have s x of s minus x of s minus 2y of s equals 0. And over here I have negative x of s plus s y of s equals 1 over s plus 1. Because x and y are now my variables. Guys, just like algebra 1. This is a 2 by 2 system with x and y being unknown. So I have my s minus 1 times x minus 2y equals 0, and negative x of s plus s y of s equal 1 over s plus 1. It's a system. Just solve the system. So easy. You want to multiply this one by s and multiply this one by 2 to kill y's? Okay, you can do that. That's going to be s squared minus s times x of s minus 2s y of s equals 0. And then the bottom one times 2, which is negative 2 x of s plus 2sy of s is equal to 2 over s plus 1. This one is also known as a grade killer because you forget to multiply this side by 2. I don't know why, but you do. And now we add the two equations which will kill y. So when I add two equations, I get s squared minus s minus 2 times x of s equal, these guys are gone, and all I have on the other side is 2 over s plus 1. Guys, I got my x. See that? It's equal to 2 over s plus 1 times 1 over s squared minus s minus 2. Well, that factors. So 2s plus 1. And this one factors into s minus 2s plus 1. With 1 on top. And we get that our xs is equal to 2 over s plus 1 squared s minus 2. There it is. I didn't do any eigenvalues. I didn't do any undetermined coefficients because of that e, right? All I need to do is another measly partial fraction decomposition, and I'm done. So partial fraction decomposition over here, we start with a over s minus 2. We'll start with this one. And then we go b over s plus 1 plus c over s plus 1 squared. Now, before you go y, it's tomorrow night. Or you go watch the videos on partial fraction decomposition from Calc 2. So now that I have this, all I need to do is work out the algebra of what I call it's like what's missing, and then we're done. So on the first one, the last one, I'm missing s minus 2. Over here, I'm missing s minus 1, s minus 2. And over here, I am missing s minus 1 squared. So now we just work this out. We know that denominators are going to cancel, so I'm not going to bother with that. And just the top is equal to 2. So I have as squared minus 2 as plus a plus bs squared minus 3bs plus 2b, yes, plus cs minus 2c, everything equal to 2. Factor out your s squares, so you have your a plus b s squared plus, can't get the linear ones, negative 2a minus 3b plus c, and get your constants. A plus 2b minus 2c equals to 2. All right. So now a plus b is 0 because there is no s squared term on this side. Negative 2a minus 3b plus c also equals 0 because no s term. Oh, I forgot s over here. Oops. And finally, a plus 2b minus 2c equals to 2. So when we equal coefficients of left and right, we get this. Okay, so the top, a is negative b or b is negative a, I don't care. So now plug that into both of these equations. So negative 2 times negative b minus 3b plus c equals 0. And negative b plus 2b minus 2c equals to 2. When you simplify algebra, that's going to be negative b plus c equal to 0. So b is equal to c. And the bottom equation is b minus 2c is equal to 2. Okay, well, we can plug this one in there now. And you get that c minus 2c is equal to 2. So c is negative 2, b is negative 2, and a is positive 2 because it has to be opposite to b. Good. I got these, which means that I can take this mess, copy it, and if tablet doesn't go crazy, paste it. Good. And I need to get rid of all of the red stuff over here because we don't need any of that stuff. We just need A, B, C, and then plug in the values for A, B, C. So A, B, and C are gone. A is 2, B is negative 2, and C is negative 2. There we go. Oh, I forgot to put f of s in front. Sorry, x of s. So this is our x of s. This is not y yet, obviously. This is just x of s. And we need to hit this with the inverse Laplace sledgehammer to come up with the x of t solution. Maybe I should move this even more in so I can put the Laplace in front. There we go. No. Here with the inverse Laplace. So now this becomes x of t. And remember that this was 2e to the 2t. And then minus 2e to the negative t. And the $1 million term. Remember the formula I said before? Somewhere up here. There it is. When you have 1 over something squared, it just gives you this t in front, and a is still the coefficient. I mean, yeah, a is still the coefficient of t in the exponent. So here's your x. And you can go and compute y now, because there is connection between x and y in the basic equation over here. So to find y, probably the top equation is better. Well, you can use the bottom equation as well. But then you have to integrate to get y, because if you plug in x as is, that will combine with this e to the negative t, but then you have to integrate so you can get y. But you have the vanilla y in this one. So x prime is equal to x plus 2y, from where y is equal to x prime minus x over 2. And you can get x prime easily, right, by differentiation. You plug everything in, and you have the solution. So x prime is 4e to the 2t plus 2e to the negative t. And now you have to do the product rule over here. So minus, product rule is copy the first one, take derivative of the second one, plus copy the second one and take derivative of the first one. So x prime is 4e to the 2t plus 2e to the minus t. And over here you have plus 2te to the negative t and minus 2e to the negative t. These guys cancel, as you can see. So your y is 4e to the 2t plus 2te to the negative t. That's your y prime. I mean, x prime, sorry. Subtract x, so minus 2e to the 2t plus 2e minus t and plus 2te to the negative t, and all of this divided by 2. What cancels here? Y is equal to, this is like, so we have 2e to the 2t. This one has no one to merge with, and the other ones are plus 4te to the 2t. No, negative t, sorry. Negative t, there we go. And divide by 2 now, you got your y of t. This is all excellent for your Thanksgiving discussions. When someone asks you, so what's new? Pull up the chair. We'll need a lot of paper. You are pretty much guaranteed not to be bothered the Thanksgiving next year if you bring this up. You can stay home, play video games, for instance. So there's your x of t, there's your y of t, and as you can see, they already have their c's computed. The undetermined coefficients thingy is already worked into this, right? That yc part that you had to do, yp part, right? So all of the stuff is worked out in the solution. There are no extra calculations. As soon as you get the solution from the inverse, the problem is over, right? There is no extra work. So we have seen a basic constant coefficients problem, which Laplace is overkill. We have seen the problems where we take like those mechanical or electrical problems, where you have also driving term, especially for electrical. Now it will be a great time to go back to that problem that we couldn't solve. If you remember, we had the second order from those Kirchhoff laws. We had the second order problems to deal with, and they had the forcing, and we didn't do that for. So now we can, because it doesn't matter for Laplace how many equations you have and whether they have forcing or no forcing, because everything gets mushed in together and algebra takes care of it, right? When you transform it. And we have seen the system now converted using Laplace. All of this was done by using that conversion method, right? You use the conversion method for the Laplace transform, where you transform the entire problem into algebraic, right? What we call a frequency domain, S domain. You converted the whole problem there, and from there you did the calculations. So that was the first part. The only thing that it's left in 7.2 is to talk about the integral transforms, because the integrals also transform, right? They also have their own transform. Now, this being the vanilla differential equations rather than being the one where you do all the proofs and derivations, right? Over here, you just shrug your shoulders and say, oh, okay, that's a formula. Okay, fine, right? But all of these, right, through fundamental theorem of calculus and that integration by parts formula that we learned in 7.1, we can derive all of that. This is not someone, you know, was communicated in a dream or something like that, right? These you can all prove, and actually, you know, for other differential equations and so on in certain schools, right, those will be the exam problems, right? Prove this formula, and then you just go and do it. So here we go with a theorem on Laplace transform of the integral 0 to t of f of tau d tau. It's just a dummy variable, and it's 1 over s Laplace transform of f of t, which is simply f of s over s. It's a very, very simple formula. And obviously, if you want the inverse Laplace, you just leave it backwards, right? So reading the formula this way, it's Laplace. Reading the formula this way, it's inverse Laplace. That's right. So read the formula either way. And that you know, that will help, obviously, with some of the problems when you are supposed to find inverse Laplace transform, and you can use this to work it out as well. I mean, if you see, right, that you got f of s divided by s, you immediately know that's the integral, because maybe you can use that as well, right, to solve a problem somewhere. See, the problem is that I don't see a problem to kind of run with it immediately and solve it this way. We can do this one. Okay, so there is a whole bunch of these problems. Actually, they're very well hidden. Problem 22 is a good one. It says find inverse Laplace for f of s is equal to 1 over s squared minus 9. All right, so can we do this using partial fraction decomposition and all of that? Yeah, you can, right? But it's partial fraction decomposition. It was going to take time. And this having the three terms, right? Because this one factors into s plus 3, s minus 3, right? You will have a, b, c variables, and you will have a lot of stuff to work with. However, if we go and deal with this using the formula above, this becomes much easier problem. So here it is, f of s equals 1 over s squared minus 9. And now we apply inverse Laplace on both sides. So the left-hand side just becomes f of t. That's not a problem. But look at the right side. You see this? Oh, come on. Do you see that that's 1 over s, and then you have this in there, and you see 1 over s right here? So what I could write here, right, when I compare, again, I am comparing this with this, and I see 1 over s in both of them. So what I can do, I have to go get another cooling pad because this one is already boiling. So what I can do here is I can write it as the integral, right? So this is going to be the integral 0 to t of inverse Laplace of the leftover, s squared minus 9 and d tau. Now, the thing inside is in a table. S squared minus 9 is going to be your hyperbolic. If you paid attention and studied the chart at all, right? When you have 1 on top and you have, well, k actually, and s squared minus k squared. Maybe I can write it. I know this is all new to you, but, right? So k, s squared minus k squared goes into cosine k, cosine hyperbolic. I can't get this, like nothing works now. Cosine hyperbolic k t. Right? So that's what you, when you have, no, it's sine. Sine hyperbolic. Sorry, sine hyperbolic. I have to go get the cooling pad because I can't even write on this anymore. It's overheated. So give me 1 second to get the new cooling pad. We have like 10 minutes of class left, but still. One more second. I just need to put this thing under the tablet. It's gonna take a few minutes for it to actually cool it off. There we go. I'm literally using ice packs to cool this tablet down with all of the software that I'm running to sustain the remote sync learning, teaching, whatever you want to call it. Those long ice packs for food. I bought a sleeve for it and everything. All right, let's see. It's kind of working. All right. So now, see, this 1 over s was peeled off with the integral, leaving just this. And now I just have that f of t is equal to integral 0 to t. And since this is a 3, I need to multiply it by 3 and 1/3. So if I multiply by 3, and I can just kick 1/3 all the way in front of the integral, I have sine hyperbolic of 3 tau d tau. And all I need to do is to integrate this, which is, again, basic Calc 1. Well, you'll learn hyperbolics in Calc 2, so whatever. That's cosine hyperbolic 3 tau over 3 computed from 0 to t. And f of t is 1 over 9, open parenthesis, cosine hyperbolic 3t minus cosine hyperbolic of 0. Now you might say, what's cosine hyperbolic of 0? And it's 1. Now you might say, well, how do you know that? Right? Crystal ball or something? Well, no, it's just cosine hyperbolic of 0 is 1 because of the definition. Cosine hyperbolic is e to the t plus e to the minus t over 2. So what you have is e to the 0 plus e to the 0 over 2. That's 1 plus 1 over 2, which is 1. Right. So the f of t is 1 over 9 cosine hyperbolic 3t minus 1. And there it is. So this is what we have for the integral transform. Again, it is useful to help us speed up some of these calculations. Now, I hope that you guys see that if you were to do over here, right, if you are to break this into s minus 3, s plus 3, that your partial fraction decomposition, which becomes a over s plus b over s minus 3 plus c over s plus 3, you see that you are going to give some form of b e to the 3t and then c e to the negative 3t with a plus in between, and whatever these c's work out to be, and b and c are gonna work out to be the same, obviously, you see the form of cosine hyperbolic 3t forming there, because I have the definition for it right here, right? And if you have a 3 in front, then each one of these are 3 and 3. But now when we plug in 0, that makes it a 0 anyway, so it drops down. So yeah, that's what we have. And even if you went the other route without the integral one, obviously it will be a lot more work with partial fraction decomposition, but you will get the same answer. I mean, you have to. It's the same problem. So we don't get to dodge that. That's it. That's all we have for our section. Now, 7.3 is translation and partial fractions, which means we're going to repeat everything we did today in terms of inverse. And then we're going to talk about translations when you are moving things around. It's not going to be a long section because we already did most of it anyway. We are going to go 7.3 and 7.4 next time, because 7.4 is going to be derivatives, integrals, and products of transforms. So those will be like when we talk about convolution and some of the other stuff that is necessary for your for your coursework later on. So that will be on Monday, right? Because the school will be closed on Wednesday, so we can have a meal on Thursday, right? So we are closing on Wednesday just in case. And then next Monday, when we meet again, we'll deal with 7.3 and 7.4. And I will probably push the chapter 8 then afterwards, so we can do that in peace, and then we can then go back and fill in the blanks of stuff that we had to skip because of the issues. Bye.